Now, next topic is pure rolling. It is a special case of translational and rotation of an object where the point of contact of the object does not slip over the surface on which it is kept, which is possible only if the velocity of the object at the point of contact is same as the surface. Let's see an example to understand it better. Now consider here is a sphere of radius r which is rolling on a plank which is also moving. Here velocity of the sphere v, angular velocity is omega, and let the plank is moving with velocity of vp. Let us find a condition for pure rolling. We have chosen 2 points A and B, one on the rolling object and other on the plank. Both these points are in contact. For pure rolling, VA must be equals to VB. That is, here is the sphere, rotational velocity is omega, here the velocity is v, here is point A, this is v, this is omega r, therefore VA that equals to v minus omega r. And for the plank, this is point B, this is VP, here VB equals to VP. As V minus omega r equals to VP, this is the required condition. What if the sphere was rolling on the fixed surface? In such case, Vp equals to 0. That means V equals to omega r. V equals to omega r is not the condition for pure rolling in all cases. It is only when the surface is fixed. V equals to omega r. This is the condition for pure rolling only if the surface is fixed. Now let us consider an object rolling on ground with instantaneous values of linear velocity of center of mass that is VCOM. Angular velocity is omega. Linear acceleration of the center of mass is ACOM, and angular acceleration is alpha, as shown in the figure. Let us find out the velocity and acceleration of any arbitrary point on the sphere. Here is the sphere. Now this is omega angular velocity. Here the velocity of center of mass, that is V of COM. This is V of COM, and this is omega R. Here also this is V of COM, this is omega R. Here is V of COM plus omega R velocity. Here the velocity is V of COM. Here is omega R. Now here is the resultant. Here is also the resultant. Here the resultant is root 2 into V of COM. Here also the resultant is root 2 into V of COM, as V of COM equals to omega R. Here V of COM, that equals to omega R. So here that is 2 into V of COM. Now d of VCOM, differentiate both sides with respect to t. That means acceleration of center of mass, that equals to alpha into r. So now let's choose an example. Suppose a string is wrapped around a disk and one end of the string tied to the ceiling and released. Find the acceleration of the center of mass. Here this is angular acceleration alpha. Here is mg. Here is the acceleration of center of mass. Here is tension T, and consider this is point P. For translational mechanics, mg minus T, that equals to ma. This is equation number 1. Now for rotational mechanics, we prefer the point of contact P, which is on the straight string. Since the torque of the tension would be 0, hence we get alpha in one equation directly, that equals to tau equals to I into alpha. That means mgr, here I is 3 by 2 mr square into alpha. That means alpha into r, that equals to 2 by 3 into g. This is equation number 2. Now A of COM and alpha are related, and the relation between them is the constraint relation. Now the acceleration of point P is 0, hence AP equals to 0. That means A of COM minus alpha r, that equals to 0. So A of COM, that equals to alpha r, that is 2 by 3g. Let's take another example. A solid sphere is projected by giving a translational velocity of v0 on a rough horizontal surface with friction coefficient mu. Now find the velocity of center of mass after pure rolling starts. Here, this is center of mass, weight is mg. Here the normal reaction force is N. Here is the friction, Fk equals to mu mg. Here is acceleration of center of mass, and here is alpha, angular acceleration. Now here Fk. Here, since the slipping starts, kinetic friction would act in the backward direction, due to which center of mass decelerates and the sphere attains angular acceleration in anti-clockwise direction as shown. Therefore, Fk, that equals to ma, that means mu mg, that equals to ma. Therefore, acceleration of center of mass, that equals to mu into g. Now, with respect to center of mass, torque about center of mass, that equals to moment of inertia about center of mass into alpha. That means mu mg into r, that equals to 2 by 5 mr square, which is moment of inertia of a solid sphere into alpha. That means alpha into r, that equals to 5 mu g by 2. Consider this is equation number 1 and this is equation number 2. As linear velocity and angular velocity t seconds later are v equals to u plus a of com into t, that is v0 minus mu gt, and omega equals to omega 0 plus alpha t. Here omega 0 equals to 0, initial angular velocity equals to 0, therefore omega equals to 5 mu g by 2r into t. Now when pure rolling starts, then v equals to omega r. That means v0 minus mu gt, that equals to 5 by 2 into mu gt. That means v0 equals to 7 by 2 into mu gt. That means t equals to 2 by 7 into v0 by mu g. Therefore, v equals to v0 minus mu gt, that means v0 minus 2 by 7 v0, that is 5 by 7 v0. This is the velocity of center of mass after pure rolling starts.